achievement. We're talking about solving a problem that has quite literally stumped mathematicians for centuries, and how a totally new approach has finally cracked the code. And this right here, this is the challenge that Professor Murad Sultan Izzuidi laid out. Now, let's be clear, we're not talking about the kind of algebra you did in high school. This is a whole different beast. Okay, so let's just dive in and look at it. Here it is. This is the monster we're trying to tame. It's a 13th degree polynomial, which just means the highest power of x you see there is 13. I mean, just look at it. All those terms, all those huge numbers in front of the x's, we call those coefficients. You can see right away why finding the exact values of x that make this whole thing equal 0 has been considered, well, basically impossible. Now, to really appreciate just how big a deal this breakthrough is, we first have to understand why this has been so incredibly hard for so long. And it all comes down to what kind of answer you're actually looking for. See, you've got two ways to solve an equation like this. On one hand, you have a numerical solution. That's an approximation. You can get a computer to just make a bunch of educated guesses until it gets close enough. And that's fine for a lot of things. But then there's the symbolic solution. That's the holy grail. It's a perfect, exact formula, kind of like the good old quadratic formula that gives you the precise answer every single time. And for complicated polynomials like ours, that has always been the roadblock. And here's why. For almost 200 years, a super famous theorem by a mathematician named Niels Henrik Abel basically said this was impossible. The theorem stated that there just isn't a general exact formula for any polynomial of the fifth degree or higher. It was seen as a fundamental limit of algebra, a mathematical dead end. But this new method, it's a direct challenge to that barrier that has stood for centuries. Which brings us to the hero of our story, Izzuidi's theorem. This is the brand new key, the special tool that can finally unlock these problems that everyone thought were unsolvable. So how does this thing even work? Well, the best way to think about it is like a special recipe. The theorem takes all those complicated coefficients, the numbers from our monster equation, and it runs them through this unique step-by-step process. The whole point is to boil down all of that complexity and spit out a new, way simpler set of coefficients that we can use to build a final equation we can actually solve. All right, now for the really cool part. Let's actually see what happens when we apply this new recipe to our 13th degree polynomial. This is where it gets good. Okay, this is really where the magic happens. The theorem is going to take those 13 original messy coefficients and transform them into a new, cleaner set of values, which we'll just call S. So what does it spit out? The first new coefficient, S0. It simplifies all the way down to just 0. Okay, what about the next one? As well. Now, this is what's really interesting. That pattern is about to break. Boom! S5 is not 0. It simplifies down to this clean, specific value, 13 to the power of 6. This is the very first crucial piece of our new, much simpler puzzle. Now we skip a few more zeros, and then we hit another critical value at 11, negative 20 times 13 to the power of 12. And that is the second key piece we need to build our final solution. And this table just illustrates the power of this method so brilliantly. I mean, look at this. Out of all the new coefficients, almost every single one of them is 0. All the incredible tangled complexity of that original equation has been reduced to just two significant numbers. It's amazing. So let's get to the payoff. How does this incredible simplification actually give us the final answer we've been looking for? Just as a quick reminder, this monster is where we started. A huge, complicated mess of 13 different terms. And this is where we ended up. That massive equation boils down to this beautifully simple form, built using only those two non-zero s values we found. I mean, the transformation is just night and day. And from this new, totally manageable equation, the roots become crystal clear. One of the exact solutions is simply x equals 0. And the other 12, they're what we call complex roots. But the point is, they can now be calculated precisely from that simplified formula. No more approximations, no more guesswork. So, okay, this is obviously a fantastic achievement in the world of pure mathematics. But what does it actually mean for the real world? Why does having a precise symbolic answer like this matter so much? Well, think about fields like physics, engineering, or computer science. Precision is absolutely everything. When you're trying to model the orbit of a satellite, or design a bridge that needs to be perfectly stable, or create a complex financial algorithm, tiny little approximation errors can add up and lead to massive failures. Getting exact symbolic solutions like this one eliminates that uncertainty. It leads to safer, more accurate, and way more reliable models and systems. And that really leaves us with a fascinating thought to end on. This new method has given us a key to a door that was locked tight for centuries. It just makes you wonder, what other problems out there, the ones we've labeled unsolved,